NASA confirmed Thursday that the Voyager 1 probe has made history by becoming the first human-made object to leave our solar system and enter interstellar space. NASA engineers assigned to the Voyager mission have been freaking out about something. The alarm bells have been coming from Voyager 1, which has been sending messages that have perplexed them for months. Liftoff of the Delta rocket carrying glass searching for unseen physics in the stars of the galaxies. After more than 45 years in space, NASA is now warning about the totally unexpected discovery made by Voyager 1. What has Voyager 1 discovered and why is it so shocking? Stay tuned as we bring you the warning by NASA about the impossible discovery made by Voyager 1. On August 25, 2012, a very important record was set, even though not noticed by the majority of the human population. For the first time ever, after a journey that took 35 years and covered a distance of more than 11 billion miles, or more than 18 billion kilometers, a human-made object crossed into what is known as interstellar space. This is the spacecraft, the first interstellar space, we made it. The object was the Voyager 1, one of the inventions that NASA is most proud of. Interstellar space is special in astronomy. It is the environment between stars. It is the region where solar winds, the stream of highly charged particles flowing out of the outer layers of the Sun's atmosphere, no longer have a significant impact on the cosmos. The region where this happens is known as the heliopause. This is the very region where the Sun's wind collides with the winds from other stars, in other words, the cold vast regions where the influence of other stars is felt. The only other human-made object to cross this boundary is the, you guessed right, Voyager 2, but this happened a whole 6 years later. To achieve this feat, Voyager 1 had been traveling at a mind-bending speed of 37,000 miles per hour, or 325 million miles per year. To understand where Voyager 1 is presently, here is a succinct description of the far away region. Imagine the heliosphere as a bubble shaped like a bullet surrounding the Sun. The Sun blasts off solar winds from its surface at about 1.79 million miles per hour. These hot, highly charged particles escape into space, filling up the void with ionized gas. This is known as helioplasma. These solar winds, however, eventually slow down and will come to a halt when they encounter interstellar space, where they find denser, cooler plasma from particles formed when stars exploded some 15 million years ago. The heliopause is practically the boundary of our solar system. When the Voyagers began their mission in 1977, scientists thought the boundary was somewhere just on the other side of Jupiter, some 365 million miles from Earth, but they actually had no idea how massive the Sun's bubble was. One of the most shocking discoveries Voyager 1 made in interstellar space is measuring the density of the interstellar medium. According to the data collected by the spacecraft, the particles in this space were higher in density compared to the outer regions of the heliosphere. The instrument that took the measurement was the plasma wave science, which detected electron density through the vibrations of plasma waves. Scientists actually expected the moment Voyager 1 crossed into interstellar space to be like a bleep, but they would learn that the boundary was much thicker and more complex than they thought. However, what they learned and observed from Voyager 1 was confirmed 6 years later when Voyager 2 also crossed the boundary. The scientists in charge of the mission were initially confused by the magnetic field data sent back by Voyager 1. They were expecting something different, like a noticeable change where the magnetic field of the Sun encountered the magnetic field from space, but they were shocked when the spacecraft did not detect any changes in magnetic field direction. Voyager 1, however, has developed a problem that threatens to bring the decades-long mission to an end. This was not the first time the spacecraft had run into problems, but the mission controllers were fearful that this might be the curtain call. However, the Voyagers have over the years managed to push the boundaries of humanity's knowledge of deep space into territories never imagined possible.
Well, let's move ahead to the launch period. John, I understand you made the decision to launch the first one and call it Voyager 2, which confused all of my brethren in the press as to why you would launch despite the naming convention. Voyager 2 took off first. It was launched from Cape Canaveral, Florida, on August 20, 1977. The launching vehicle was a Titan Centaur rocket. Voyager 1 took off on its own spectacular journey about 2 weeks later on September 5, 1977. Voyager 1, however, was able to reach its planetary targets faster because it launched on a faster, shorter trajectory. Even though they might have been overtaken by modern inventions, the Voyagers were a marvel of their time. They carried onboard sophisticated modules that allowed them to study, record readings, and transmit them back to Earth. The Voyagers were crammed with instruments that studied the atmosphere, magnetosphere, moons, and the rings of the planets they came across. These instruments included magnetometers, infrared and ultraviolet spectrometers, cosmic ray and charged particle detectors, and a sophisticated imaging system that could send back photographs that revealed what the other planets in our solar system looked like in detail. The administrator, however, included some items that would puzzle anybody knowing about the Voyagers for the first time. They loaded a golden record containing sounds and images. The purpose was to introduce humans as a species to any potential extraterrestrial intelligence that might come across them. The initial trajectories of the Voyagers were a result of careful calculation that just had to be precise. They were meant to take advantage of a window that opens once every 175 years. It was the case of a rare planetary alignment that allowed the mission handlers to use gravity assist to boost the spacecraft speeds and fashion their path through the outer solar system. This was a very novel approach at the time, and fortunately, it worked. Voyager 2's path included flybys of Jupiter and Saturn before cruising towards Uranus and then Neptune. Voyager 1, on the other hand, was planned to move steeply away from the ecliptic plane after executing a close flyby of Saturn. The trajectory would bring it close to Saturn's biggest moon, Titan, which scientists were interested in because of its dense nitrogen-rich atmosphere. The spacecraft would then change course as it shifted to its final mission, exiting the solar system and heading into interstellar space. Would the scientists of the 70s, with the technology available to them at the time, be able to achieve this, or were they punching out of their league? The first question was how to keep the Voyager spacecraft moving and functioning for decades without running out of fuel. Voyager 1, like its sibling, actually had a propulsion system that did not focus on sustaining thrusts but on accurately correcting trajectory and precisely monitoring orientation as it hurtled through space. It is because of this design that the spacecraft can both navigate and position its instruments and antennas correctly. The Voyager 1 has a propulsion module that contains 16 hydrazine thrusters that are packed in 2 sets of 8. One set controls the attitude while the other set manages correction maneuvers. The spacecraft stores the hydrazine in a tank and supplies it to the thrusters through a network of pipes. Inside each thruster, a hydrazine interacts with a catalyst, causing it to decompose into hot gases and be expelled to generate thrust. But what about the power on board? How has the power source managed to last decades? This is the secret to the exceptional longevity of the Voyager spacecraft. Each of them has a radioisotope thermoelectric generator, or RTG. No, it has nothing to do with solar, and that was for a glaring reason. The spacecraft would reach places where the solar intensity would be too weak to power the various components. The RTG works by converting the heat produced when a radioactive material decays into electricity with the help of thermocouples. You probably guessed right, thermocouples are devices that convert heat or thermal energy into electrical energy. Voyager 1 carries 3 RTGs, each of them using plutonium-238 dioxide as the radioactive material. NASA chose plutonium-238 because it has a favorable half-life of 87.7 years. This meant it could theoretically provide a decay heat source steadily and reliably for long periods. The Voyager initially produced about 470 watts of electrical power, however, as the plutonium decayed, the power output has dropped. But the good thing about the setup is that the rate of degradation can be predicted and managed. For example, because of the steady drop in power output, NASA has been shutting off some of the instruments that are not needed. Among the first to go were the cameras, as the spacecraft is now in total darkness and the cameras cannot see anything. However, the vital components are still up and running, and that is why NASA can still receive and send data to Voyager 1, including uploading updates to the operating system. Voyager 1 started making returns on investment in terms of scientific knowledge early into its interspace journey. One of the ways it has enriched our knowledge of the cosmos was its flyby of Jupiter, which helped astronomers to see the jumbo planet in ways it had never been seen before. On March 4, 1979, NASA's Voyager 1 spacecraft took the first photos of rings around Jupiter. For example, astronomers were astounded when they realized Jupiter had rings. Before the flyby, nobody knew about the existence of the rings. However, Voyager 1 made a discovery of a thin, flat ring floating around Jupiter, proving that Saturn was not the only planet in our solar system festooned with rings. Voyager 1 detected more than rings. It returned a wealth of information about Jupiter's atmosphere. From the data and images returned, scientists were able to confirm the presence of complex cloud forms, swirling storms, and rapidly evolving atmospheric patterns. But one of the most iconic things Voyager 1 discovered on Jupiter was the Great Red Spot. The spot is actually a storm that has been blowing for centuries, and the storm is so massive it is larger than the Earth. Jupiter's red spot is a gigantic cyclone larger than the size of the Earth. Voyager 1 provided close-up images that showed us the intricate wave-like structures the storm is made of. In fact, the spacecraft allowed astronomers to take measurements of the storm, and they discovered that the Great Red Spot rotates counterclockwise. It also had a period equivalent to 6 Earth days. Another thing that astronomers discovered for the first time on other planets was lightning in Jupiter's atmosphere. It just didn't occur to them that lightning could take place elsewhere apart from Earth, but Voyager 1 showed that the thunderstorms on the largest planet in the solar system were very similar to those on Earth. The thunderstorms on Jupiter are also formed from the heat rising from the interior of the planet. However, the lightning flashes were significantly more frequent and intense than what we see on Earth. It was the proof that astronomers needed that Jupiter has a dynamic and volatile atmosphere. Another discovery made by Voyager 1 on Jupiter was about the planet's magnetic field. According to the readings taken by Voyager 1, Jupiter has a magnetic field that is stronger than was hitherto estimated. In fact, it was by many dimensions more powerful than Earth's magnetic field. This knowledge helped researchers to better understand the interaction of Jupiter's magnetosphere and solar wind and charged particles. For the first time, scientists realized that Jupiter's massive magnetosphere had huge swirling currents that were carrying charged solar particles. Before Voyager 1 departed Jupiter, it also studied Jupiter's moons. Again, the information Voyager 1 sent back to Earth was completely unknown at the time. On its approach to Moon Io, Voyager 1 took images showing prominent volcanic plumes shooting into space. Some of these plumes extended as far as 300 kilometers above the Moon's surface. It was the first time an active volcano was spotted on another object in the solar system, and the plumes were so large that they were noticeable against the backdrop of space. The picture even showed where the most spectacular of the plumes came from. They came from a volcano named Loki Patera on Io. The heat from these volcanoes was detected by infrared sensors. Voyager 1 also grabbed pictures showing hundreds of volcanic calderas. Some of them were filled with molten sulfur or sulfur dioxide, with stunning hues ranging from yellow to green, black, and red. The volcanoes prove that Io has a core that is super hot enough to sustain the amount of volcanic activity. The discoveries on Io were instrumental to understanding the ring encircling Jupiter. Actually, it was the material ejected from Io that formed the ring, but it gets even more exciting as the tour surrounding the Jovian planet interacts with the planet's powerful magnetic field to create high-level radiation belts and auroras on the jumbo planet. But perhaps the greatest of discoveries ever about moons was made by Voyager 1 on Europa, another of Jupiter's moons. Can you imagine a moon containing an ocean under a layer of ice? The images of Europa taken by Voyager 1 showed scientists a landscape patterned with crisscrossing lines. The lines or markings had different colors, with a reddish hue being the most prominent. Another thing that surprised scientists was the surface of Europa. Europa is very old as a celestial object, so researchers expected the surface to be filled with craters or marks as a result of many strikes by meteorites, but the photos sent back by Voyager 1 showed relatively few craters, which could suggest that Europa was relatively young and therefore geologically active. Another suggestion was that there was something erasing the craters, likely the effects of a shifting crust or the flow of icy volcanoes. However, the greatest discovery was the presence of an ocean under the surface. With the way the ice was fractured and young, the scientists were inclined to conclude there was the possibility of liquid water, which would have formed from the moon's internal heat melting the ice. This opens up a lot of possibilities. Could this body of water contain life, making Europa one of the places most likely to host microorganisms apart from Earth? This has been a tantalizing possibility that researchers have been working tirelessly to ascertain. Voyager 1 also made a detour to observe Saturn about a year after completing its Jupiter mission. It encountered its second planet. Here, too, a lot of surprises were waiting for the spacecraft to unlock. Voyager 1 targeted the F-ring, a feature of Saturn that was discovered the year before by another NASA spacecraft named Pioneer 11. Voyager 1 discovered some moons occupying the space between the rings. The spacecraft also discovered previously unknown moons associated with the second largest planet in the solar system. The new moons were Atlas, Prometheus, Pandora, Rosalind, and Belinda. But more interesting was the moon Enceladus, which was found to reflect more sunlight than any other object in the entire solar system. It made astronomers conclude that there was still geological activity going on within the moon. Later missions showed that Enceladus contained geysers shooting up water and ice particles, hinting that there might be a subsurface ocean. The big question, however, is what will happen to Voyager 1 and its twin. The power source won't last forever. In fact, NASA is already preparing for a scenario where the RTG is shut down or cannot provide enough energy to power the spacecraft and its components. At that point, Voyager 1 will continue to journey through space, reaching places that no other human-made object will ever reach, continuing as a silent representative of the human race long after we are gone.